just here at the beginning, as I've chatted with many of you over the past couple of days, a common question has emerged, which is, what the heck are we supposed to do with this peptide stuff that's not in the book? So let me try to answer that in the way I told some of your peers. Basically, my purpose in talking about this stuff in greater detail was to give you an example of how what you've learned in OCHEM is the key to unlocking biology at the molecular and the atomic level. I want you to understand the idea that atoms and bonds are related to larger biomolecules and their structure and their function. So, what does that mean in terms of what you have to do? The stuff we went in deeper depth in is not in the text, it's covered a little bit, but not in as much depth as we did. But what do I expect you to have learned from all of that? Well, do you need to memorize the individual Ramachandran plots for each amino acid? No, clearly not. I have in the past written a question where I said, okay, well, here is a protein secondary structure, and at this particular position is an amino acid, and it works best when that amino acid has a phi-psi angle of plus 60 and 0. So, of all the amino acids, which should I put there? And then I give you, and then I would give you a table with all of these individual plots. And you'd have to look at them and see which one would best fit that context. So, because I know the answer, we'll just zoom in. Glycine is the only one that has a large amount of examples where it can adopt a dihedral angle of plus 60 and 0. So you'd say, okay, we want to put glycine there. So that's no memorization, but it is using data. And if you have no idea what phi and psi are, it's going to be difficult. If you have no idea what a Ramachandran plot is, it's going to be difficult. If you don't know that phi is on the x-axis and psi is on the y-axis, it's going to be difficult. But if you've thought about these issues, you should be able to handle it. With the amino acids and structures, what would I do with that? Well, on a multiple choice exam, I can't say, draw for me the structures of all the 20 amino acids. I mean, I could, but that would be boring. So what I will do instead is I will say, here is an amino acid sequence in one-letter codes. Maybe it's 20 amino acids long, maybe longer. The pH is 7.5. What is the charge on this peptide? Right? And so it's going to be like the question you had on exam 1, only you don't get the side chain structures, and you also don't get the pKa's, and you got to figure that out. So you've been warned, practice. All right. So we've been talking about how to make peptides in solution. I want to move on to carbohydrates today, but we've got a little bit more to do with peptide synthesis. The reason we're talking about how to make peptides chemically is because that process has enabled a whole ton of really, really useful biomedical research. And it's been enabled by chemistry. So our problem in making amide bonds with amino acids was which nitrogen is going to react with which carboxylic acid in the DCC reaction. So to prevent undesired side reactions, we've talked about a protecting group for carboxylic acids. This will temporarily mask the carboxylic acid, so it's no longer able to react with DCC, no longer able to form an amide bond. But at a later stage, when we do want to perform a reaction with that group, we can easily remove the benzyl ester using hydrogen and palladium on carbon. This is an ester, so you could also do acid-catalyzed ester hydrolysis, and that would work just fine. Now, at the same time, we want a protecting group for amines, and it needs to be not removable by hydrogen and palladium on carbon, because we might have a peptide where we wanted to unmask a carboxylic acid without touching the N-terminus because we want to bring on another amino acid at that point. So the protecting group that we're going to use of choice for the amino group is called Bach. Did we talk about Bach on last time? Okay. Okay, so done. Couldn't remember. All right, and Bach is removable by TFA and water. All right, so now our scheme for solution of a simple dipeptide is we take one amino acid that we want to modify the acid group, and we will protect the amine as the Bach group. That will prevent the amine here from being a nucleophile in the peptide or the amide bond forming reaction. Then we will protect this carboxylic acid as the benzyl ester. That will prevent this carboxylic acid from being activated by DCC in the amide bond forming reaction. So the only two functional groups available for chemistry here are the carboxylic acid on this Bach-protected glycine residue and the amino group on this benzyl ester-protected alanine residue. So then we do the reaction, DCC and triethylamine. That's a way earlier in this semester nucleophilic acyl substitution reaction. We make the new amide or peptide bond, and we have a protected dipeptide. Okay? Get the idea. The protecting groups have prevented undesired side reactions. Now, at this stage, there may be, go ahead. DCC is dicyclohexylcarbodiimide. That doesn't help. So it's this reagent. And this probably doesn't help either. So you'll need to go back to chapter, I'm not remembering. Yeah, go back to the chapters in Exam 1. It may be chapter 16. Or look at the index or search your text for DCC. But what this basically does is it modifies the carboxylic acid so that the OH becomes a really good leaving group. And then nitrogen can attack to give a tetrahedral intermediate, and then the leaving group gets kicked off. All right. So depending on what we want at this stage, we can do multiple things. So suppose we wanted just to isolate the dipeptide, but we don't want the protecting groups on it. We'll need to do what I will call global deprotection. That is deprotection of both groups. And so there's a couple of ways you could do this. One would be to use hydrogen and palladium on carbon to remove the benzyl ester, and then TFA and water to remove the Bach group. And that would give you this dipeptide. Alternatively, and I think this is something your text uses, is just acid-catalyzed ester hydrolysis. The acid conditions would remove Bach, but would also remove the benzyl ester. So you may find your text doing things like whatever conditions they prefer for acid-catalyzed ester hydrolysis, which will also remove Bach. Okay, so that's if you just want the dipeptide. But suppose you wanted to add another amino acid. At this stage, you have to decide whether you want to add the amino acid to the N terminus of the peptide or the C terminus of the peptide. N refers to nitrogen, C refers to carbonyl. And so suppose you wanted to modify on the N terminus. What you would do is first Bach deprotect with TFA and water. That would liberate the amino group and allow it to be a nucleophile in a subsequent step. And that's when you would introduce another amino acid. I'm just, for the purposes of this, I'll just throw in leucine. This is Bach-protected leucine, and you'd react this, and you'd need DCC and triethylamine to make the amide bond. Oops. And what you would get after these two steps is now the fully protected tripeptide. Where this is leucine, glycine, and alanine. And then if that were our target, we would do global deprotection. If it weren't, we could add on additional amino acids. Alternatively, suppose we wanted to do C-terminal modification. What we would do is first remove the benzyl ester group, and we would have to do it in a way that does not touch the Bach on that dipeptide. We don't want this to be a nucleophile in the next reaction. We want to use a different amino acid. So we will remove only the benzyl group. Whereas before we removed Bach. And then in a second step, we would bring in, this time, not a Bach-protected amino acid, but a benzyl-protected amino acid where the amino group is not protected. And that's going to give us, after the reaction with DCC and triethylamine, that amide bond forming reaction, that's going to give us this different tripeptide where the N-terminal amino acid is glycine, followed by alanine, followed by leucine. Okay, so and these are two different molecules, depending on they're very similar, but their sequence is different, and they could presumably have different structures and/or functions. But our protecting group strategy gives us a lot of versatility. We can make the peptide longer on the N terminus or the C terminus, or we can stop where we're at with the dipeptide. Okay, yes?
So if we want to remove both sides, we can use the acid-catalyzed ester hydrolysis, but we only want to remove the ester, we would have to use H2.
Right. If you only want to remove the benzyl ester, you've got to use hydrogen and palladium on carbon. If you only want to remove Bach, you've got to use TFA and water. If you want to do both of them, you would use those acid-catalyzed ester hydrolysis conditions. Okay. Others? Yeah?
What specific mechanisms do you want us to know?
What mechanisms do I want you to know? There's no new mechanisms here. You can go back and review the DCC mechanism, though I don't think we actually did that in a lot of detail. If it helps you to remember how the reaction happens or what happens in the reaction, that could be worth some review so you don't get confused. Attaching the Bach group is an example of mechanisms we talked about in chapter 16 and 17. Putting on the benzyl bromide is an example of an SN2 reaction that you did in 351. So it may be worth a little bit of review, but there's no new mechanisms here. All right, what else? Yeah?
If you were to put like your second projecting group after you put the log on, would there be like another reaction that happens, or would it still react with the...
Okay, so if I weren't to remove what? Sorry, I missed that.
If you have your bar amino acid, but you don't put on your like benzene like protecting group on the other one, would you still get like a formation, or like...
Okay, so I think the idea is, I'm sorry, I'm struggling. If you removed Bach and then added this, but this one didn't have Bach?
Like,
I'm sorry, I'm so dense.
like if you had like your two amino acids you're trying to combine, but one of them didn't have like their protecting group.
Oh, right. So if you tried to do that, say I'm using this glycine residue and then I'll use this alanine that is benzyl protected, yeah, I'm going to get the desired dipeptide, but I'm also going to get two glycines added to each other, and perhaps more than that. Yeah. Okay. So this process works really well. This iterative strategy of deprotection and then coupling on of the next amino acid and so on. But imagine you want to make a peptide that's 30 amino acids long. All right, so that's 60 different reactions if you don't count all the having to protect the various amino acids. 60 different reactions to do it one by one. And if your yield on each step isn't like 99+%, you're taking a number like 0.8 raised to the 30th power, and that starts to get small pretty quick. And so your yield drops off precipitously. So most people who are making peptides via this method are stopping around 10 to 15 amino acids long. But there are some problems along the way. First problem is purification. If you look at my starting material for one of these subsequent coupling reactions, I have this protected dipeptide, and then my product is this tripeptide. Part of what I have to do after the reaction is I have to isolate my desired product from any unreacted starting material if my yield is not 99% or higher. And their polarities might be such that they're difficult to separate. And so purification at each step is a challenge. It becomes even more so if I try to use a time-honored technique for maximizing the yield of a reaction, which is to just use a huge excess of one reagent relative to another. So suppose the individual amino acids are cheap, but the dipeptide is difficult to make. I would want to throw 3 to 5 times excess of my amino acid to drive the reaction to completion. So that may bump up my yield, but I still have a purification problem because even if the yield is 100%, if I use 3 to 5 times excess, I've got a lot of extra amino acid floating around that I have to isolate or I have to get away from my desired product. So the purification issue really is kind of problematic. One way that people have tried to sidestep this is to make shorter peptide segments, 3 to 5 to 7 residues or so on, and then link those together in segment coupling reactions. So imagine taking this tripeptide, removing the Bach group, and then taking this tripeptide and removing the benzyl ester group. Then using DCC and triethylamine, combining these two, you should be able to get the amino group of one to couple with the carboxylic acid of another, and then I have a hexapeptide, and I didn't have to do 6 steps linearly. I made 2 tripeptides and then brought them together. There are some technical problems with that as well, but they can be overcome. And in the early 60s, a chemist at Merck named Ralph Hirschman synthesized a 128 residue, well, he and his team synthesized a 128 residue protein called ribonuclease A. And after synthesis and removal of the protecting groups, they found that it folded and adopted the right shape and had enzymatic activity. And this was one of the early experiments that demonstrated that for a lot of proteins, you just need the sequence of the amino acid to specify the proper fold and function. Somebody else had demonstrated that earlier, a chemist by the name of Charles Anfinson, who won the Nobel Prize. He basically took ribonuclease A and boiled it to the point where it should be unfolded, and then let it cool down, and it regained its enzymatic activity, which indicates that even from an unfolded state, the sequence of the peptide or protein contains all the information necessary to adopt the correct shape. Okay, questions so far? Yeah.
Can you make a long peptide? Can you take two shorter, like, I don't know, peptides are usually 10 length long and then put them together?
Yeah, that's called segment condensation, and you can. There's a stereochemistry problem with that approach that's not worth talking about in this class, but that maybe limits how easy that is to do. You also have a peptide solubility problem. I've chosen side chains that are mostly soluble in organic solvent. I haven't talked about solvent at all, but usually the solvent we use is DMF, which is a polar but non-protic solvent. If you start to introduce a lot of side chains that have polar functional groups, the peptide can get less and less soluble, and so solubility is sometimes an issue for longer coupling of segments together. But people still do that, and this approach works, especially when you want to make large quantities of short peptides. So the Michaelis lab is doing this all the time. And they can make multiple hundreds of milligrams quantities of peptides, which is actually an astronomical amount of peptide. For the experiments we do in my lab, we don't need nearly that much. Okay, so let's talk about an alternative. Go ahead, sorry.
I was just going to ask, like, on the rare chance, could you ever get like an intermolecular reaction between your peptides?
Yeah, could you cyclize? Sure, and people want to do that too. So actually, if you cyclize 1, 2, 3, 4, 5, 6. So if you deprotected this and deprotected that, and then it did a DCC coupling reaction, you would have just made a 6-membered ring. And those things I think are called diketopiperazines, and some of them are important biomedically. But yeah, you can make cyclic peptides as well. All right. So the yield and purification problem. So also in the 60s, at the same time that Hirschman was at Merck, sort of brute force trying to hammer out this 120 amino acid sequence in solution phase, a chemist at the Rockefeller Institute named Bruce Merryfield, he won the Nobel Prize for what I'm about to describe, was thinking there's got to be a better way. And he is the inventor of solid phase synthesis. Now, the idea is this. What if, instead of having your peptide in solution, what if you had your peptide attached to a macroscopic bead of something that was insoluble in organic solvent? And what if you had your amino acid here? And then what if you added a Bach-protected amino acid that's free on the carboxylic acid end, and you added DCC and triethylamine? And what if you used 3 to 5 times excess of this? So you mix those together in this reaction vessel, and we will use squiggly lines for the peptide chain that's still present on these beads. And then in solution, we would still have lots of amino acid because we used an excess. And the excess of the amino acid is going to drive the coupling reaction to completion such that we get a really high yield of the desired dipeptide. Oops. But then at that stage, rather than have to worry about purification, because your desired product is attached to this macroscopic bead, you simply put a filter disc at the bottom of this flask, filter disc, and the filter disc has pores that will let out the stuff that's in solution, but not the macroscopic beads. So you're going to drain off the solution, and what you'll be left behind with is your reaction vessel with your filter disc at the bottom and all of your peptide containing beads, but none of your excess amino acids. That gets filtered out and washed away. So with one brilliant insight, Merryfield invented this method that you could use very simple and easy. You could do very simple and easy purification. And you could also make the reaction super high yielding because you used an excess of an amino acid. So you get the idea. We do a reaction, but purification's easy because the thing that we want is physically attached to something that you can actually pick up with tweezers or filter out with the filter disc. So suddenly purification became a lot easier. Yeah?
How difficult is it to actually attach it to that bead?
Right. How difficult is it to attach it to the bead? And the other question is, how do you get it off? Because though there are some uses for polymer beads that have peptides attached to them, in a lot of cases we want to actually study the peptide or protein on its own, so we have to have some way of getting it off the resin. You need a way to put an amino acid on, and then you need a way of taking the peptide off. And if you think about the coupling conditions that we're going to use, this reaction would involve, this approach would involve basically a series of iterative steps. Once you got to this stage, before you proceeded to the next step, you would need to do Bach deprotection, which is with TFA and water. That would take this peptide and remove the N-terminal Bach group, unmasking the nucleophile that you want to use in the next step. Then you would need to do a coupling step with the next Bach-protected amino acid, whatever it is. And again, you could use, oops, that's the wrong stereochemistry. Again, you could use DCC and triethylamine to make the amide bond. And then after that stage, you would have your tripeptide. And so you could continue onward, iterating between coupling and deprotection steps until you had made a peptide of very long length without having to even do deprotection, or without having to do a purification step. I'll point out that in between deprotection and coupling steps, we do a thorough wash of the resin beads using some organic solvent that will remove the reagents from the previous step. So Bach deprotect, wash the resin. Coupling step, wash the resin with an organic solvent. And by doing that, you always get to hold on to your desired peptide, but you wash away any of the other unreacted starting materials and anything that might interfere with the subsequent reaction. All right, but think about the chemical requirements for this bead. This bead and the linkage between bead and resin are going to see TFA, which is a strong acid, so they need to be stable to TFA, but they're also going to see triethylamine and DCC, so they need to be stable to that as well. And there needs to be a convenient way at the very end to cleave your peptide off the resin. So let me show you a little bit about Merryfield's approach. The polymer he chose was polystyrene, and polystyrene consists of 2 carbons and an attached phenyl group, that so that in the polymer you have alternating carbons with phenyl groups on them. All right, and Merryfield's idea that you do this, you can make this via radical polymerization, and often there are cross-links between individual polymer chains. Merryfield's innovation was, instead of just using the styrene precursor, which is the benzene ring attached to a double bond, what if I also included some styrene derivatives with a functional group on it that I could do chemistry with later on? So instead of polystyrene, the Merryfield resin basically had this same structure and same properties, but every once in a while, and billions and trillions of times per individual polymer bead, one of these phenyl groups would have this benzyl chloride on it. Okay, so now you basically have a bead with a functional group on it that we can modify and that we can attach an amino acid to. So the Merryfield resin is a polystyrene bead, a phenyl group, and then this chloro leaving group at the benzyl carbon. All right, so now you can begin to see how we could attach a peptide to the resin. In a lot of ways, this reaction is going to be exactly the same as benzyl protecting a peptide, like we did above. So you would take this polystyrene bead, and you would need a mild base to deprotonate a Bach-protected amino acid to the carboxylate, and here's whatever side chain. And then the reaction simply an SN2 reaction where the carboxylate acts as a nucleophile, the leaving group, the chloro leaving group leaves, and in the end I have my amino acid now attached to the resin. And now I'm ready for all of the subsequent steps. So this is an easy-on chemistry. It's quite easy to do. In fact, it's easy enough that a lot of people, instead of buying Merryfield resin, will buy resin that has the first amino acid on, because if it's so easy, you just as well have robots do it, right? Okay, so now let's talk about cleaving the peptide from the resin. So after you've done the synthesis, and oops, there is, sorry, and you've got your long peptide chain, and this works for things that are 30 to, this works pretty well for things that are 30 to 50 amino acids long. Thankfully for all of us, I'm not going to draw one that's that long, but you get the idea. Much longer peptide chain. Once we finish, we usually remove the Bach group on the N-terminus, and then cleaving from Merryfield resin works with hydrofluoric acid, HF. And I believe it's sort of a another SN2 reaction. Likely you protonate the carbonyl oxygen, and then fluoride comes in as a leaving group and kicks off your peptide. And this works really well, and afterwards what you're left with is your desired peptide. And at that stage, when you after you've done the cleaving reaction, your resin stays in the flask, and what you drain out is the solution of HF that has your peptide in it, these little squiggly chains, and then you have to isolate the peptide from that HF mixture and purify it. And this works really well, as I said, for making peptides that are quite long, 30 to 50 residues routinely, and even longer than that sometimes through special effort. But the challenge here is that HF is dangerous to work with. If you've ever taken a chemical safety class, they'll tell you that if you get even a drop of HF on you, it's a very, very serious thing. Your life is in danger, and you have to take immediate steps to save your life. The fluoride gets into your bones and starts binding up calcium, and it results in massive bone weakness, and it's a really, really, really bad way to go. So a lot of people were skittish about using this technology because it involves such a dangerous reagent. Now, people that actually do this say that it's not that bad. You have to have special equipment to deal with it, but if you're properly trained and know how to deal with the hazards, it's not that big of a deal. Nevertheless, the difficulty of using HF was such that not a lot of people adopted this chemistry. For the first, I would say, 10 to 20 years after Merryfield's discovery, the people who were doing this kind of chemistry were people that had been trained in his lab. But then later on, a new protecting group was invented that facilitated the design of a new resin that could be cleaved under different conditions. So your text introduces a protecting group called FMOC. And you should look at that and learn about it. It's not that hard to understand. We won't talk about it in a lot of detail. But the FMOC group is cleavable by base, and it's a protecting group for the alpha amino group of the amino acid. And the base that's typically used is an organic soluble secondary amine called piperidine. And the fact that you didn't need to use TFA for the Bach deprotection steps, for the amino group deprotection steps. Remember, in Merryfield's original method, you used TFA to get rid of Bach and then do the coupling reaction. But the fact that now you could use basic conditions meant that we could redesign this linker such that it would not cleave with HF, but rather with a strong acid. So the FMOC strategy involves a base labile alpha amino protecting group, and then on the resin, it involves an acid cleavable linker, not just HF cleavable. And the innovation was, I think, inserting oxygen in the bond between resin and your benzyl chloride. What the presence of this oxygen makes the ring electron rich enough that at the end of the day, when you have your peptide here, you can use TFA, and that protonates this, and then this oxygen will kick electrons down and literally kick off the peptide as a leaving group. So combining base labile FMOC chemistry with an acid labile resin peptide linker enabled everybody to sidestep the use of HF. And so for FMOC chemistry, the steps are very similar. You do a deprotection reaction using piperidine. That removes FMOC. And your book will take you through this in more detail. And then you rinse, then you do a coupling step exactly the same way, only you're using an FMOC protected amino acid. And then you do a rinse step, and then you repeat as iteratively. And then at the very end, you cleave your peptide from resin using TFA. And no need to ever see or think about or interact with HF at all. So this is what we do in my lab, and the FMOC chemistry has really made this approach accessible for even non-experts. So undergrads in my lab routinely do this. I've taught high school students to do it before, and they become very proficient. There are even machines that can do it, and they actually do it better than humans because machines don't make mistakes unless you tell them to. All right, questions? Yeah.
So in the FMOC reaction, I can see like why the benzene ring is there, but in just a regular HF reaction, is there a main purpose as to why they were shooting the benzene attached to your study?
Here?
Yeah.
I think the purpose was to have a leaving group that could be incorporated easily into the polystyrene resin. So the benzene ring is, I think, to match the structure of the resin. But then you have a leaving group that's a primary alkyl halide that should be easy to modify with an amino acid. And here, what's here is another benzene ring and linked to the polystyrene, but this new linker, you can remove the peptide in conditions that are not lethal. Yeah. All right. Others? Yeah.
With the original resin, why couldn't you break the bond between the beads, let's say, and the peptide chain through hydrolysis?
Why couldn't you do it through ester hydrolysis?
Like the side chains, like
Um,
for example, that also has the side chain.
I don't know. That's a great question, and I actually don't know the answer. My guess is that they were probably worried about the ester hydrolysis conditions also hydrolyzing amide bonds in the peptide, though that's not a huge issue, so I'm not sure. One other thing that I should mention that we haven't talked at all about is some of these side chains have nucleophilic groups on them. And we've ignored that, but chemists can't afford to. What if at the stage you go to do a coupling reaction, where are we? What if at the stage you go to do a coupling reaction, this side chain is a lysine side chain and has an amino group? Which amino group is your next amino acid going to go on? Will there be selectivity? Probably not. There's a chance for undesired products. So part of all of this is the design of side chain protecting groups that are stable to TFA and stable to coupling conditions, but will come off in HF for Bach chemistry, or that are stable to piperidine and stable to coupling conditions, but will come off in acid for FMOC chemistry. We haven't talked about any of those, but it's just know that it's out there, and if you ever come up to my lab and look at the amino acids that we have in the fridge, their names are going to include side chain protecting groups, and that's why. All right, well, that's more time than I wanted to spend on the subject, but it's also something that's near and dear to my heart, and I've been doing peptide chemistry since the early days of 2004 when I joined the Gelman group at Wisconsin. And everybody that makes a peptide screws up at least their first peptide, and often many. I have ruined many peptides. If you don't follow this procedure exactly, if you forget to deprotect, then your next coupling reaction fails because your amino group isn't nucleophilic. But you don't know that it failed, and you don't know that you forgot it until you get to the very end, you cleave your peptide from the resin and discover it's not the right stuff. So in order to do this, you have to have meticulous attention to detail. We have this elaborate system in my lab where we write down the sequence, and then we put a little check mark when we've done a deprotection reaction, and another little check mark when we've done the coupling reaction, and try to keep track of what we do. Because if you miss any one of these steps, the synthesis will fail, but you won't know that it failed until the very end. So it's a lot of wasted time. There are also machines that can do this. We have an automated peptide synthesizer in the department. It's upstairs in my lab. It's pretty easy to use, though there are some technical problems. But it's really nice to be able to walk up and basically program in an amino acid sequence, and then it makes it for you. But in a pinch, and if we're using expensive reagents, we do this kind of chemistry by hand. So, all right. Well, I'm sorry that we spent so long on that. I wanted to talk about carbohydrates, and what we'll have time for is just a brief introduction into carbohydrate chemistry, which is chapter 24. Carbohydrates are sugars. Their general molecular formula is CnH2ON, which means that for every carbon you have 2 hydrogens and 1 oxygen. It's like a hydrate of carbon, and therefore carbohydrate, right? Carbohydrates, as I said, tend to be sweet, but if you ever go do carbohydrate research and publish a paper in a journal about your research, you will be tempted to, and you'll think you're really punny, you'll be tempted to use the word sweet in your title, like Sweet Chemistry, the story of whatever. It was cute the first time and probably the first 3,000 times. It is no longer cute, so you should avoid that temptation. I know that will apply to basically none of you, but I have to do my patriotic duty and suppress that pun. All right, so we're going to do a lot of stuff that's in your text in this chapter. There is also a lot of stuff in your text that you have almost zero chance of actually using in your life, that stuff that I haven't even ever used, and if I don't use it, you're really unlikely to use it. So we'll focus on the things that will come up in future biology environments. I'm going to draw for you the structure of something called beta-D-glucopyranose. Now, that's the correct name, though what most people call this is just glucose. Though technically, glucose in and of itself is incomplete. You need some more detail. We're going to draw the structure that glucose adopts in aqueous solution, which is most of biology. It's a 6-membered ring that adopts a chair conformation. One of the atoms in the ring is an oxygen. Then we're going to put OH groups on carbons 1, 2, 3, and 4. And those OH groups will be equatorial. Then on carbon 5 is not an OH group, but rather a carbon, a CH2 group, which is attached in turn to an OH group. Carbon 5 actually does have an OH group, it's this oxygen here. But this is the structure of glucose, or rather beta-D-glucopyranose. Each part of this name has an important feature that tells you about the structure of this molecule. We'll talk about the meaning of each of these. But before we do that, I want you to look at this structure and note that it is a hemiacetal. If you've forgotten what that is, you need to go remind yourself. This is a cyclic hemiacetal. You have a single carbon bonded to 2 oxygens. One is an OH group, one is an OR group. And the carbon that's bonded to those 2 oxygens will have a special name in carbohydrate chemistry. We're going to call it the anomeric carbon. Now, I want you to go and convince yourself that glucose, if it weren't an acetal in its open form, would be an aldehyde. That'll be a good review of cyclic hemiacetal stuff. So prove to yourself that glucose is an aldehyde. And we'll see you on Friday.